This short lesson is on the work-energy theorem. Energy is sometimes defined as the capacity to do work. This definition doesn't make any sense unless you know what work is. Well, it turns out work is a transfer of energy by a force. So the work done by a force is equal to the magnitude of the force times a displacement of an object as the force acts upon it, times the cosine of the angle between the force and the displacement. So let me give you a more specific case here that will hopefully help you understand this equation. Here's an incline. There's a box on the incline. It's being pulled by tension in a rope by a person. So let's look at the forces acting in this example and the work done by those forces. So let's consider the forces acting on this box and the work done by those forces. There's the force of gravity, which points straight down. There's a normal force, which points perpendicular to the incline. And there is a tension force, which points along this rope. In this problem, we'll say the weight of the box is about 100 newtons. The normal force is about 86.6 newtons, and the tension in the rope is also about 100 newtons. To find the work done by the tension force, we need to know the magnitude of the tension force, we need to know a displacement of the box, and we need to take the cosine of the angle between the tension force and that displacement. Let's consider a displacement of 2 meters. So now the work done by the tension force, the tension was 100 newtons. Multiply that by 2 meters. And notice I used a delta x here for displacement. That could be a delta y, it could be a delta z, it could be a two-dimensional vector. X is meant to be just a generic variable here. And then for the cosine, we need to decide what angle we're using. We're kind of used to going after the angle of the incline, but in this case, the angle we want is the angle between the force vector, which would be here along the tension, and the displacement vector, which is here up the ramp. The angle between those two vectors is 0. And so we're taking the cosine of 0. So the work done by tension here, we have 100 newtons times 2 meters times the cosine of 0, which is 1. So the total work done by the tension is a positive 200 units of newtons times meters. Well, in this case, that's energy. Those are joules. So what does it mean to say that tension has done a work of 200 joules? Well, what that means is that the force of tension has transferred 200 joules of energy to the block. Where did this energy come from? Well, it came from the person who's providing the tension, which transfers energy from the person to the block. And we've calculated that 200 joules of energy have been transferred by the tension force. So now let's talk about the work done by the normal force. So the work done by the normal force is equal to the magnitude of the normal force, which was 86.6 newtons, times the displacement, we're considering a displacement of 2 meters, times the cosine of the angle between those. Well, what's that angle? So normal force points perpendicularly to the surface of the ramp, while displacement points parallel to the surface of the ramp, which means the angle between those is 90 degrees. Now, cosine of 90 degrees is 0, so the work done by the normal force is 0. It doesn't matter how strong the normal force is, it cannot transfer any energy into or out of the system, which is the block in this case. We have one more force to consider, and so that's gravity. So we're going to consider the work done by the force of gravity. That's going to be equal to the force of gravity, which is 100 newtons, times the displacement. We're considering a displacement of 2 meters, times the cosine of the angle between them. So that angle, the force of gravity points straight down. The displacement points along the surface of the ramp. So the angle between these is related to the angle of the ramp. It's going to be 90 degrees plus that angle of the ramp. So if we call the angle of the ramp 30 degrees, then the angle that we're taking cosine of is 90 plus 30, so that's a 120 degree angle. When I calculate this, I find that the work done by the force of gravity in this case is a negative 100 joules. So energy is a scalar, it's not a vector, there's really no direction. So what does it mean to have a negative sign? Well, this means that the force of gravity is taking energy away from the box. As the box moves up the incline, the force of gravity has taken away 100 joules from the energy of the block. Work is the transfer of energy by a force. We've examined a scenario and considered the work done by each force acting on the box in this scenario. Tension force transferred 200 joules of energy from a person to the box. Normal force does not transfer any energy because it acts in a perpendicular direction from the direction of the box's displacement. The force of gravity transferred 100 joules of energy from the box to the earth. So we can consider a total work done. The total work done is the sum of the work done by all the individual forces acting. And it turns out the work-energy theorem tells us that this total amount of work is always equal to the change in kinetic energy of the system. So for this scenario, the total work done turns out to be a positive 100 joules, because we had a positive 200 plus 0 plus a negative 100. So the change in the kinetic energy here should be 100 joules. And I'd recommend that you think about calculating that for yourself. But on the next slide, I will go through how you can do that. So I'd like to check that the change in kinetic energy in this situation is equal to 100 joules. So here's a reminder. Change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. And kinetic energy is calculated by 1/2 times the object's mass times the object's velocity squared. So that means delta K is equal to 1/2 mass times V final squared minus 1/2 times mass times V initial squared. Well, these 1/2 times mass things, those are the same. And so I'm actually going to factor those out. So delta K, the change in kinetic energy, is equal to 1/2 times 10 kilograms was our mass. All that times V final squared minus V initial squared. Well, I don't know what the V initial was, but turns out that doesn't matter. If you're new to physics, you'd probably be pretty tempted to give up at this point because you don't know V initial, you're not sure how to get V final. I've seen this problem before, and once you finish watching this video, you've seen it too, so you'll know. Don't give up. Don't give up. Here we go. We still keep this 1/2 times the 10 kilograms out here. But now the magic happens. We're going to use kinematics. To find V final squared, we're going to use a kinematics equation where V final squared is equal to V initial squared plus 2 times the acceleration, which I can actually get from the force analysis. That would be 5 meters per second squared in this case, times the displacement, which is 2 meters, and that's V final, and then I'm going to subtract off V initial squared. Well, check it out. I've got a V initial squared, subtract a V initial squared, they're gone. Gone. So all I need to do now is put in these numbers, calculate these numbers. The change in kinetic energy is equal to 1/2 times 10 kilograms times 2 times 5 times 2, and I find that the change in kinetic energy is equal to 100 joules. Done. So we have just used an example to illustrate, prove, really in a way, the work-energy theorem. I hope work and energy make just a little more sense to you after watching this.